Thank you very much. Okay, so thank you so much for your assistance and welcome guys. So my name is Stefano Tebaldini. I'm a professor at Politecnico di Milano, and I will be giving this first lecture about the basics of SAR and of tomographic SAR. So basically, just a foreword about this lecture. The idea is that this first lecture has to be inclusive. So it is thought for everyone here, independently on your background. This will mean, of course, that for SAR experts, this is going to be a bit boring. So I hope not too much. I hope that I will convey new concepts or new perspectives also to SAR experts. But the intention is that everyone has to understand how a radar works. So, especially, I think that things in technology have to be understood from the inside. So I will use a few equations. I will talk a little bit about physics, but if I do my job well, at the end of this day, you will be happy and you will feel that now you are stronger in this field. So let's see if I get it correctly. So we start from the very basics. Radar. Radar stands for radio detection and ranging. And this is a technology, as the name says, to detect and study far-off targets, basically by sending an electromagnetic wave and receiving the backscattered echo. There are some relevant features that we have to highlight. First, it is an active instrument. So in remote sensing, there is always this distinction between active and passive. So a passive instrument is an instrument that just sense what is already there. So like a camera, you get an image because of the sunlight. Not so a radar. A radar is an active instrument, so it transmits its own source of illumination. It's based on delay. So, and I think that this is a thing that has to be kept in mind. Radars can become very, very complicated. You can have setups where you have many different radars with some bandwidth or frequencies and in a weird geometry. But if you really want to understand what a radar can give you, you need to think that it always measures a delay. And this delay is then converted into a distance based on the knowledge of the speed of light. Importantly for us, we deal with microwave instruments, so waves that can be with a wavelength of, say, from some 70 centimeters down to 3 to 1 centimeter, more or less, for a radar. And in this regime, microwave do penetrate into rain and clouds. So in this sense, we say that radars have an all-weather visibility. So it can sense the Earth largely independently on the weather conditions. And importantly, the microwaves can even penetrate into some natural media. This is the case of forests, snow, ice, sand, which gives you a sensitivity to the whole three-dimensional structure of those media. Now, we talk about SAR. What is a SAR? SAR stands for synthetic aperture radars, and it is basically a radar. Broadly speaking, let's say it's a normal radar that is just installed onto a moving platform. So as the platform moves, a platform like a satellite, or it can be a car, can be an aircraft, can be a drone, whatever you like. As the platform moves, the radar transmits its signals and receives the backscatter echoes. And in so doing, with some sophisticated digital processing techniques, which we will see today, we are able to generate an image. So let's say that the output of a SAR image, of a SAR survey is an image that can be quite extended of the Earth's surface as it is perceived in the microwave regime. Now, this first lecture, by means of this technology, we can generate different applications. One is topographic mapping, land mapping in general, change detection, or deformation monitoring. And this is by virtue of some key features of SARs, basically penetration through rain and clouds, synthetic aperture, which is the key to having a fine resolution, and it's a phase preserving system. Now, I will not insist on this notion of phase preserving, but let's say that since it's phase preserving, then you can measure displacement with an accuracy of centimeters or even millimeters from space. But there is more to it. And this is that microwaves penetrate into natural media, as we said in the first slides. And this is the case of like snow, forest, vegetation in general, ice, sand. And this basically means that when you look at the SAR image acquired over a forest, say, you have to think that each pixel, so the number that characterizes each pixel in this image, is actually the contribution. Sorry, I'm fighting with this microphone. Let's see if it works this way. So this means that each pixel is actually the result of the contribution of every target, of every scatter, let's say, of every object that is in this region. So let's say that is found at the same distance from the radar trajectory. For the case of forest, it means that within a single pixel, you have the ground, you have the lower canopy, you have the top of the canopy, and so on. And here is where the concept of SAR tomography pops in. With SAR tomography, that is a technology that is built by using different SAR acquisitions. So let's say that you take data from, in this case, from 3 trajectories. We will use many more, but let's say just to visualize it from a bunch of trajectories. What you have to do is to process the signals from all the different trajectories coherently. So we do a sort of a super processing of all of the data at the same time. And in this way, we can resolve the target at different elevation. So I like this representation. Just imagine that this balloon here is the area that contributes to the signal in each pixel in a SAR image. So each pixel is the result of everything within this bluish balloon. Well, for tomography, it's no longer about pixel, it's about voxels. And so the balloons here means that you can resolve the terrain, you can resolve the mid canopy, the top of the canopy, and so on. And this is an example of how it works. Those are real data, and from a tropical forest. In this case, this is a SAR image of just the ground, so the scattering from just the ground level, from 10 meters within the forest, from 20 meters within the forest, and for 30 meters. So let's say that you have the ground, the lower canopies, mid canopy, and the top of the canopies. And this, of course, is represented by, so we call this a tomographic cube, because you can imagine that if you have many different images, you put them together, then you have a sort of a cube. And so this is what we are going to see today. Here is a first example. Okay, now this Zoom is blocking the title of this slide, but this is an excerpt from the first airborne demonstration of SAR tomography by Reiber and Moreira from DLR. This is from year 2000, so some 23 years ago. And this is a representation of what was there. So spruce forest, buildings, cars, and a corner reflector. And this is a vertical section. Up there is a vertical section of what is seen by a tomographic survey. So you see the forest, the buildings, and so on. Ever since then, there was a lot of research about tomography. Here is a very brief history of SAR tomography. Let's say that the principle was formulated in the mid-90s. Then we had the first airborne demonstrator in the year 2000. And since 2007, there was a lot of activity on SAR tomography, and this was pushed by space agency, in particular ESA, DLR, and JPL, to have airborne campaign or ground-based campaign to investigate this concept, in particular for vegetation, for ice, snow, and for agriculture. Next year, if we'll be lucky, we will have the launch of the P-band mission Biomass, and this will be the first mission with a systematic tomographic phase dedicated to forestry. So Biomass is there to produce the first 3D vision of forest worldwide at P-band, of course. For the near future, let's say that we have great hopes in bistatic systems. So let's say formations of different satellites working together to do this also at higher frequencies. Some examples, just to show you from the very beginning what we are talking about. Here is a tropical forest. Those are data from AfriSAR, acquired in Gabon. This is a SAR image, and here we have 3 transects, so 3 vertical cuts, where you can see the profile of this forest. You see that it is like swaying up and down. And why? Because in this case, the focusing was done with respect to a flat terrain. So we see the topography of the forest, and we also see the forest. Maybe it's a bit more clear if I overlay the those white lines representing the terrain elevation below the forest and forest height. You see how the match is good. And basically, by this principle, we can analyze those transects to get products, so to get biophysical products. One first product is forest height, and this is something that you can basically do just by tracking the upper part of those transects. And this is the forest height by SAR tomography as compared to forest height by a laser sensor. We can also get terrain topography below the vegetation, and this is an interesting product. We can use this to attempt to classify the forest structure. This was a paper by DLR where they reconstruct the forest structure based on an indicator of the horizontal and vertical structures. So we do not dwell into details here. And another application is to estimate forest biomass. Now, there's been a lot of talks about forest biomass. Forest biomass is named the AGB, so the above ground biomass. This is a very important biophysical parameter. It is necessary in so many applications, including climate studies, because it is a key indicator for the carbon cycles, and it is still largely unknown at global scale. Now, the idea is that radar, especially a low frequency radar, can estimate or can be sensitive to above ground biomass. But it turns out that since a single pixel within a SAR image is sensitive to everything, so to turn scattering, to scattering from the mid canopy, from the top of the canopy. So since everything is mixed within a SAR pixel, we have a decreased sensitivity. So one idea that was tried a few years ago was to try to split the forest into different layers by tomography. And so we have the image for the ground scattering, image from the mid canopy, image from the top of the canopy, and simply see in a sheer experimental fashion which layer was the most responsive to forest biomass. And this is what we saw, basically. This is the correlation of a SAR image to forest biomass. So there is some correlation, but not too much. This is the correlation for just the ground. There is a slight negative correlation. There is not so much correlation for the mid canopy, but there is a very good correlation for the layer at 30 meters. So this was a finding that if we are able to split, to single out the contribution of just some part of the forest, then we can largely increase the sensitivity to forest biomass. And this was repeated in different forests and also at L-band for the case of boreal forest. Another example where having a tomographic SAR is a good idea is in the investigation of glaciers. In this case, we have a beautiful aerial picture of the Mittelberg-Ferner Glacier. And this is how it looks like from tomography. In the top panel, you have a GPR. So the top panel is not a SAR, is a GPR, is a ground penetrating radar. So basically the top panel was generated by taking a low frequency radar and by walking it on the surface of the glacier, which was quite scary because of crevasses. The lower panel here is what you can get from airborne tomography. So basically they flew many times over the glaciers, and with signal processing, this transit was generated, and it's a great finding to see that you can identify the presence of fern, crevasses, the bedrock, and so on. This is, and now we have, okay, this is now an example of polarimetric SAR tomography, where each layer is represented in false color. You can notice that at the top, we have a certain polarimetric signature. So there is a certain polarimetric response. As we go down, the color changes, which means that the polarimetric response is changing. And this is a movie that we generated to impress the young students. The information is of course exactly the same. And yet another example is snow. This was an experiment that we had. This was by Laurent and myself, by the way, an experiment we had in Austria in 2013, so 10 years ago. So we are also getting old, by the way. And we tried to install a tomographic SAR. In this case, it was a ground-based tomographic SAR, just to see if we could understand the structure of the snowpack. And the answer was yes, very well. And the result was that we could detect different layers within the snowpack. And we were lucky because we had the availability of handmade profiling of the snow. So we had the sort of a ground truth to compare with, and turns out that the radar is actually sensitive to any change of structure within the snowpack. So And okay, and finally, my list of examples has to mention biomass. This is an impression of the biomass satellite. Here is the P-band antenna, the umbrella. And biomass, as we said, will be launched next year. So sometime next year. And it will provide the first 3D coverage of forest worldwide. Now, finish with this first list of examples. Let me try to change the mic because this one is terrible. Okay, magic. Thank you very much. Okay. Much better. And let me also do this. Okay, so we are finished with what we can do with SAR tomography. We start now with how to do it. And of course, basically, our theory so far was just about saying that radar is an active instrument and blah, blah, blah. And by virtue of this, we can generate all this array of products. So very good, but how to do that? Well, let's say that we need some efforts concerning the geometry of radars, waves, and some hints about radar processing. So this is where we go now. Is the audio okay for you? Can you? Okay, thank you very much. So we start with waves. What is an electromagnetic wave? Well, very shortly speaking, an electromagnetic wave is a perturbation in the intensity of a static field. It is an effect of the universal speed limit, and we can say that it is triggered by charges, by electrical charges in non-uniform motion. So let's say that if I have a charge in my hand, if I start shaking this charge, this will produce a wave. And very importantly, the waves, electromagnetic waves, always propagate in free space with a constant velocity, which is the speed of light. Representation. So we need some mathematical tool to represent waves. The way we do this is by considering some signal S. So S, just imagine any function, just a pulse that goes up and down. And this is a function of time and space as t minus z over c. And now we will see better what this means. Let's say that when we express a signal or a wave as a function of just time, we are intending that we fixed the position in space. And so we analyze the wave in a single position. So for example, we have here the transmission and reception of a signal. If we read the wave at 0 meters, then we have this signal, so just an oscillation. If we read the signal at 50 meters away from the transmitter, then we have this other signal. It's S of t minus 50 meters over c. And so basically you have a delay or a shift, if you like. So the same thing is happening a few microseconds later. When we say that we fixed that we express a signal in space, it means that we fix the time now. So just imagine that we want to take a snapshot of a wave. So we fixed the time. In this case, we fixed the time at 83 nanoseconds. And this is how the wave looks like in space. So now it's a function of space. We can mix the two representation. So for example, I consider the very simple case of a monochromatic wave. A monochromatic wave, it means that your wave from S is just a sinusoid. So it's a cosine of 2 pi f0t. F0 is the frequency of this sinusoid. And this is how the sinusoid appears in time and space. So you have space is horizontal, time is vertical. The color scale is such that red means a positive crest and blue means a negative crest. We can analyze two sections. So if we take a section at 35 meters, so a fixed position in time, then we analyze the signal in, a fixed position in space, then we analyze the signal in time, or we can fix the time, so 117 nanoseconds, and we analyze the signal in space. The temporal period is the inverse of the frequency. The spatial period is also called the wavelength, and this is given by C over f0. Now, with this very simple background about waves, what we need, so the next ingredient that we need to bring in is about the geometrical principle of localizations. Remember that all a radar does is to sense a distance. And now what we want to do now is to take this concept. So I can get hold on the distance of an object from me, and we want to expand it. So step by step, we will use the simple concept to create a radar image or radar boxes. So I start from a very simplified description. So I say nothing about hardware, antennas, and so on. Just imagine that you have some antenna here, the red triangle. We call this a radar. So it just transmits a wave. This wave goes everywhere around. Just imagine a circular wave on the water surface. And it reaches some point in space. Let's say point 1. We have just seen that we can express a wave as S, the waveform of t minus the distance over c. So if P1 is at a distance r from our radar, the wave as it is at P1 is S of t minus r over c. And this is it. But what happens if in position P, it was P1, sorry. What happens if at position P1, there is something that we call a target that is able to reflect the wave? Now, the actual physics of scattering is absolutely not trivial. But the good thing is that we can always imagine that a target that receives a wave is a new generator of waves. So basically, the waves hit the target, and the target now generates a new spherical wave. So it's like having another source. So we have now a new source that is reaching any other point in space, let's say point P2, and we can express the signal at point P2 as the signal of t minus r prime plus r over c. So the total delay is given by the total distance traveled by the wave. So from the radar to the target and from the target to the point where we are measuring. Now, if the point where we are measuring is the radar itself, it just means that we have a delay due to the fact that the wave is traveling from the radar to the target and then back to the radar. So we have a total delay that is twice the distance over the speed of light. And in this way, this is how a radar can tell you the distance from a target. Let's say that this is the transmitted signal. It's just a peak. It goes. Just imagine an amplifier that is off
then it goes on and then off again. As simple as that. And this happens at 5 microseconds. Then the wave goes to the target and gets back to the radar. And we get the same peak after 25 microseconds. So the delay, the radar has instrumentation that is able to tell you this delay between transmission and reception. This delay is 20 microseconds. We know the speed of light. And so this means that this particular target is found at 3 kilometers away from the radar. So basically, we trade time for space and we can tell the distance, which means that after a radar survey is performed, a survey with a single radar, what you know about the target is that it has to be found over the surface of a sphere that is centered on your radar and with a ray that is given by the distance that we have just measured. So in this sense, we talk about a one-dimensional localization. After a radar experiment, you are sure that the target is found onto the surface of this sphere. Now, we start with the SAR. We install this radar onto an aircraft and we just let it fly. What happens? It happens that from any position along the trajectory of this radar, you have transmission, reception. So basically, you have one radar experiment for each position along this trajectory, which means that you can measure the distance of the target to different points along this trajectory. So geometrically, what we can say is that the target has to be found in the intersection of all the spheres that are centered in the trajectories and with the radius that you are measuring. Now, the intersection of all the spheres, this is a sheer geometrical exercise, is a circle. And this circle is always perpendicular to the trajectory, and its radius is given by the minimum distance. This is also called the closest approach distance or the zero Doppler distance. Okay, this is just a radar jargon. But this is important that if your experiment is about having a radar on an aircraft that flies, then you have a two-dimensional localization capability. And you are sure that after this experiment, if you process the data correctly, your target has to be found here, somewhere in this circle. The information that you're still missing is the angle, is the elevation angle. And how is this solved? Well, just imagine that you fly now multiple trajectories. So for each trajectories, you have a circle. If you do the intersection of all of the circles, finally, you have just a single point. So for this reason, tomography that is built by flying multiple trajectories provides you with three-dimensional localization capabilities. Now, so far so good. I always like this geometrical approach. This is where I start with everything in my lectures. Because it provides you, I think, with a very robust, with a very solid understanding of why radars can be used to localize targets in 1, 2, or 3D. But of course, geometry only unveils these very basic principles, but it doesn't say anything about what is the resolution of my measurement. So of course, I do not expect that I can tell the position of a target to within a nanometer accuracy. So what is the resolution? How can I resolve different targets? And in general, what if there are many targets around? Because so far we are just assuming a single target. So to understand this, we need to go a little bit into the physics and the mathematics of radar signals. So now we want to see how a radar signal looks like. So our mathematical model is STX-RF. So a very sophisticated notation to say that TX is the transmitted signal, so what is sent by the antenna. RF is radio frequency. So it is a radio frequency signal. What does it mean? Basically, you can build a radio frequency signal by taking any pulse. This is called G of T. Again, this is our very simple pulse. The amplifier is off, then it goes on, and then off again, but multiplied by a cosine. In this case, we have, this is how the signal looks like at with a frequency of 435 megahertz. This is how the signal looks like with a higher frequency. Now, how do we choose the frequency? Well, this is a big question. Let's say that the frequency is perhaps the most important parameter for any radar survey. It will determine which antenna it has to be used. It will determine what kind of hardware has to be used. And very importantly for us, because we are interested in not so much in engineering today, but in science, it will determine how the target respond to our waves. So this is a very famous example by Madame Letoin. This is how an Austrian pine can be imaged to be. This is how the same Austrian pine responds at X band. So let's say that in the very first approximation, we can imagine that if the wavelet is short, then we are just sensitive to the top of the canopy. This is the same at L band. In this case, we are not sensitive to the leaves, but we are sensitive to branches. At P band, an even longer wavelength, we are just sensitive to larger branches. And if we go at a very long wavelength, so a very low frequency, then it can be modeled as a simple stick. So let's say that the frequency is everything. It's the first thing that you need to understand for your experiment. But we are interested here just in the mathematical aspect. So the frequency is just a parameter. Bon, we have, this is our transmission. Now with the oscillation that depends on the frequency, we say that when the target responds, we have a delay. And so this is this received signal, where the delay is given by twice the distance over C. Now, with some basic but boring and tedious trigonometry, you can express the received signal in this way. It is always composed by two members, by two factors. The one is what multiplies the cosine of 2 pi f 0t. The other one is what multiplies the sine of 2 pi f 0t. And this is called by electronic engineers the in-phase component and the quadrature component. When we receive a signal, we are actually interested in getting our hands on the in-phase and the quadrature components. And why? Because you see that the information, so what we don't know, the reason why we want to perform a radar experiment is all embedded in the two in-phase and quadrature components, which means that the A is just an amplitude factor that is telling us how strong this target is, and D is the delay that is telling us the distance from the radar. There is no interest in the cosine and sine terms because we already know the frequency. So we want to extract those two components. And indeed, electronic engineers have built machinery to do that. So basically, we get a radio frequency signal, and there is a thing called a receiver that is able to do this job for you. This information is embedded as a numerical signal, as two numerical signals. So it's written in a computer, it's written in your hard disk in the form of two numerical signals. And now those two numerical signals are summed after multiply one by the imaginary unit. And so what we are going to see now is all about complex numbers. So I hope that you are not frightened by complex numbers. I tell you, the real reason why every physicist, every engineer, everyone who has anything to do about waves uses complex numbers is that it simplifies your life a lot. If you remember a trigonometry from high school, I always had to have my handbook to remember all the formulas. And in this case, you need to deal with the sine and the cosine. So you need to remember how to sum them up, what is the difference of a sine, the sign of the difference, and blah, blah, blah. Well, if you just work with complex exponentials, you don't need to do that. Everything comes out easily. But of course, you need to accept that you are representing two signals as a single signal, but it is complex. So for those who have a background in engineering or physics, this is quite natural. For those who haven't, don't worry, you will get familiar with this. So basically, this is what we consider our received signal. It's I plus JQ. And now we see why it provides you with a noticeable simplification. The received signal is simply expressed in this form. You have a pulse with a delay, and then an exponential, a complex exponential. Oops, sorry. Okay, whose argument is called the phase. Now, if we recall that the distance is given by twice the distance, that the delay is given by twice the distance over c, that the wavelength is c over the frequency, we have this simple representation where you see now all the important factors are just here before our eyes. So the received signal can always, and this is an absolutely general expression, is always written as an amplitude factor. This is telling us, so if A is big, it means that our target is perhaps a truck. If A is very small, it's perhaps, I don't know, a fly or something. We have the pulse. This is the pulse that we have transmitted, and this pulse has a delay. So this delay is telling us the distance. And then we have the complex exponential. Its argument is called the phase, and the phase is where the magic starts. Now, I think that we have some time now to go into the frequency domain. How many of you are familiar with Fourier transforms? Okay, so some of you, but not all of you. Very good. So I'm very happy about this because I prepared a few slides on it and I wasn't sure it was necessary, but it is. Very good. So when you study radars, you will hear a lot of times words like bandwidth, resolution, and the engineers say, the bandwidth is not enough for the resolution that we need to have, or the spatial bandwidth is not enough for the angular resolution that we need to have. And so to understand what this means, you need a short introduction about Fourier analysis. And so the topic seems to be complex, but I think that you can grasp the basics today. So basically, the signals that we have represented today, that we have seen until now, were all given in the time domain, which means as a function of time. We just imagine that the time goes by and we have the signal, and we can visualize the signal going up and down. But we can as well say that our signal can be written, can be built as the sum of a certain number of sinusoids. I call the sinusoid also a complex sinusoid. So the exponential of j2 pi ft, for me, this is a sinusoid as well. It is called a generalized sinusoid. Okay, let's say that we like to write a signal as a form in the form of the sum of complex exponential. So we can imagine that this signal G contains a certain number of frequencies. So it's built, is constituted by a certain number of frequencies, and that the amplitude factors, the G1, G2, and so on, represent the strength by which any of those frequencies contribute to G. The question, of course, is, can we play this game for any possible signal? So is this a generalized representation? And I let Dr. Richard Feynman answer. The short answer is yes. We can represent any signal in the form of a sum of complex sinusoids, except some crazy signal that only mathematicians can dream of. But for all physical signal, we are sure that we can play this game every time. And this is just an example. This is a signal that I want to use. This is what I get with the sum of just 3 sinusoids, the sum of 13, 27, 37. When I sum up 77 sinusoids, then I get the same signal. So this means that I can represent a signal either in the time domain, so as a function of time, or in the frequency domain. What does it mean? That instead of representing the variation of the signal in time, I just tell you the strength of the sinusoid at every particular frequency. So this graph is to be read as the sinusoid at 0 Hertz has a strength of, what is that, 3 something. The sinusoid of 100 Hertz has a strength of 2, and so on. If we sum up all the sinusoids with those strengths, then we get back to the original signal G. How do we, oh, sorry, and very importantly, what is the bandwidth, finally? Well, the bandwidth is simply the interval of frequency that are substantially larger than 0. So we can say that the signal has a bandwidth of 1 megahertz. It means that we need an interval of 1 megahertz to get all the frequency that we need. And let's say that for radar pulses, with some exceptions that I don't have time to discuss today, but let's imagine that this holds. We can say that the signal bandwidth is always the inverse of the signal duration. So a very short pulse has a very large bandwidth, and vice versa, a very long pulse has a very narrow bandwidth. How do we get to know which frequencies contribute to a given signal G? The answer is the Fourier transform. This is the Fourier operator. It's given in many ways in book with the integral or with the sine, the cosine, with exponential, with the 2 pi. You can give it in frequency or in angular frequency. It's always the same thing in different clauses. How do you build this? Basically, you take your signal. Just imagine that the signal is read at fixed times Tn. You multiply by a complex exponential at the frequency that you want to analyze, and you sum. The result is exactly the term G of f that gives you the strength of this signal. And of course, you need to compute this sum for any frequency that you want to study. The computer does it for you, so it's not a big deal. Now, with this in mind, we can now come to the important concept of range resolution. So you see, we start from the basics of wave, then with some geometry, and finally we can talk about resolution. So we are getting into physics slowly. What is range resolution? Well, resolution is a very important concept. Resolution is not measured in pixels, as I say the first lecture to all of my students. So the resolution is not how many pixels you have in your camera. The resolution is the capability of a sensor, of an instrument, of an analysis to resolve, namely to distinguish two objects at a given distance. So let's say that I can more or less count you, so I have a resolution of 1 seat, more or less. If you were farther away, then my eye resolution would not suffice. Mathematically, how do we express this? Well, waves are a linear phenomenon, at least in the regime we are interested in. And so we can say that if we have two targets and not just one, then the received signal is the sum of the two received signals that we would have with just a single target. So we have the delay for target 1 with its phase, and the delay for target 2 with its phase. Now, if we visualize the magnitude of this signal, we would expect something of this kind. So now we have not just a single peak, we have two peaks, one for the blue car and one for the red car. Now, if I see two peaks, then I can fairly say that, okay, there are two things out there. There is a first target at distance R1, and there is another target at distance R2. So if this is true, then we can say that I am resolving two targets. And we can state a condition for this to happen. We say that the duration of a process is 1 over the bandwidth. So we can distinguish two peaks as long as the difference of the two distances is larger than this value, than C over 2B. And this is called the range resolution of your system. If this is not true, meaning if two targets are found at distances such that their difference is lower than this value, you can visualize it. It just means that the two peaks overlap, and they would form just a single peak, based on which you could not tell that there are two different things. So this is just to give you some example. I think it's always very important to have some feelings about the numbers. Biomass, the biomass system, due to ITU regulation, will implement a bandwidth of just 6 megahertz. And with 6 megahertz, you have a range resolution of 25 meters. A typical L-band SAR can have a bandwidth of about 40 megahertz. I think that this is the bandwidth of SARCOM, and which means that the range resolution is some 3.75 meters. The case of an airborne SAR at low frequency is typically about 100 or 150 megahertz, which means a resolution of 1 meter. This is also the case for a high frequency spaceborne SAR like Cosmo or TerraSAR-X. They can as well implement an even larger bandwidth. So with a 500 megahertz, you get to a resolution of 0.3 meters. if you go to very high frequency radars like automotive radars or military radars, then they can have a bandwidth of a few gigahertz with which you can get a range resolution of a few centimeters. So this is just to give you some feeling about the numbers. Now, let's talk about the angular resolution. So now we have attached the physical meaning to our first 1D experiment, where we have a single radar, transmit, receive. We saw that we can resolve two targets as long as the distance is consistent with the range resolution of our system. We said in our geometrical interpretation that if we fly a radar, then we can have also an angular resolution, meaning that we can pass from the surface of a sphere to the border of a circle. Now, let's see why. And to do that, I need to take a step back. So we forget about the bandwidth for the time being. We just assume the case of a monochromatic wave, which basically means that we transmit just a cosine without any pulse. And in the complex domain, we imagine that we transmit a complex exponential, and so we receive this signal. A monochromatic signal means that your pulse is, the g of t is just 1. So this is the form of your received signal. We forget about the delay component. We just have amplitude and phase. And we imagine this time that we have multiple radars. So we have the radar 1, transmit, receives, radar 2, transmit, receives, radar 3, and so on. The target is not moving, of course, so it's just a static scenario. And so our signal is given in this form. For the antenna number n, we receive a signal whose phase is given by the distance from the target to the antenna number n. So we have a variation of the received signal just because the antennas are in different positions. Now, let's put some geometry in. The distance after the car, we know that we can write the distances in this way. Well, probably even after Archimedes. And so this is our expression. There is a square root. We usually do not like square roots because they are not linear, and it's difficult to make calculations with a square root. So what people do, even if they don't expressly tell, but what everyone does is to linearize this expression. So basically, if we imagine that the target is far away, and by far away, I mean that its distance from our set of antennas is much larger than the size of our array. Just imagine that we have an array of 1 meter and the target is at 100 meters. Well, then it makes sense to approximate the expression of distances in a linear form. And in this case, we have a constant, let's say the distance from the central element, plus a variation that if you do the math, it's very simple, depends on the sign of the of this angle. So the variation of the phase along your array from one antenna to the other depends on this angle. So now we can write it. Okay, just to mention, this is equivalent to approximating a spherical wave to a plane wave. And when you hear people talking about the far field, this is more or less what they mean. So under this approximation, the target is very far with respect to the size of our array. Then we can approximate the distance in this way. So we can tell that the received signal for the different antennas can be written in that way. And you see that we have in the phase, just look at the term that is changing with R. It is the exponential of 4 pi over the wavelength times the sine of this angle times the exposition of our antennas. Well, if you just create a new concept of frequency, no longer a temporal frequency measured in hertz, but now a spatial frequency that is measured in meters to the -1. We say that we invent that there is a thing called the frequency of the car, and this is twice over the wavelength times the sine. So if we rewrite the problem in this way, then we can say that the exponential term is just that the phase in the exponential term is just describing a linear variation, so a variation with x, with the antenna position, that is analogous. It is exactly the same mathematics as a frequency in time. This frequency is called f car, and basically, if we get to know this frequency, then we get to know the angle under which this car is seen. So we have a signal. Now it's no longer a signal as a function of time. This is a signal as a function of space. We have said that under suitable approximations, this signal can be modeled mathematically as a frequency, as a sinusoid with a certain frequency. We want to know this frequency. We have just seen it. When you suspect that the signal contains some frequency and you want to know which one, what you do is you compute the Fourier transform of this signal. And this is exactly what we do. If we do that, we have a situation like this. Here we have the signal along our array. You see, I express the varying part just as the exponential of -j2 pi times the frequency of the car times x, so the position of the antenna. I calculate the Fourier transform, and this is done exactly as we did it in time. What we expect is that we should visualize a peak. We have just said that this signal contains a single frequency, right? So we would expect to see a single peak because the Fourier transform is the mathematical operation that we do to visualize which frequencies are contained within the signal. We get this single peak, and based on this single peak, based on the fact that we know the law of conversion between frequencies and angles, then we can tell the angle under which this car is seen by the array. Okay, this is exactly what we do, and believe me, if you understand this, then you are in a very good position because, for example, automotive radars work exactly this way. And also SAR is not so different. Now, what is the last concept that we have to bring in before the coffee break? Well, we spent some time talking about bandwidth and resolution. We saw that if a signal has some duration in time, so a duration of t seconds, then its bandwidth is more or less the inverse of this duration. So now we should wonder, okay, fine, what is the duration of this signal? Which is a weird question because now the signal is not in time. The signal is in space because our signal here is a variation of the phase over space. So which is the duration of this signal? Well, let's say that Oop. Okay, let's say that I have to jump. Okay, let's say that this signal has a spatial duration, which is given by the length of the array. So we have a phase that varies over space, which is the duration of the signal. Well, it depends on the region of space over which we are sensing, we are observing the signal. In this case, it is the total length of our array. So if this is the signal duration, then it means that in the other domain, in the frequency domain, the signal has a bandwidth, and the bandwidth is the inverse of the duration. So we do not get a single peak as we would expect, but we get some spread. So the peak is, we get something of this kind. And this spread is basically given by the inverse of the spatial duration of the signal, so by 1 over A. Okay, so I think we came to a good point. It's 10:15. We all need a coffee, so we can take a break and we reconvene in 30 minutes. Thanks. We have coffee, no? Oh, good. So, C'est reparti, oui, c'est ça.
Il faut appuyer.
Mais c'est moi qui l'ai fait.
Ok, c'est fait.
Enregistrement.
Are you sharing? Okay, and you're sharing the screen. So. You need to share the screen.
Ah,
Otherwise, we will only record.
Otherwise, we'll just see this.
We make écran. And that's it.
okay, great.
Thank you.
And now you are in full panorama.
Okay, so here we are. Last thing we saw was about this. Thank you. So last thing we saw was about this concept of bandwidth. So we have duration and bandwidth, which in this case is declinated in space. So we have an observation space that gets converted to a spatial bandwidth. And again, so as the concept of temporal bandwidth led us to the important concept of range resolution, now we have that spatial bandwidth will bring us to the concept of angular resolution. And we reason exactly in the same way. So we say that there are now two targets. There's a car and there is a tree. And those two targets are even at the same distance from the sensors, but under two different angles. So if we play the same game, so we compute the Fourier transform along the spatial dimension, then we get two peaks. And by seeing that we have two peaks, then we can tell that there are two targets at different angular positions. What is our capability to, when do we lose our capability to distinguish or to resolve two peaks? Well, when the two peaks overlap, which means when the angular positions of the two targets are so close to one another that the two peaks overlap and we just see a single peak. In this case, our instrument does not have enough resolution for us to tell that there are two targets. And again, we can cast a condition. So we can say that the difference of the frequency of the car and the frequency of the tree has to be larger than the frequency resolution of our system, which is the inverse of the length of the array. And so if you do some calculation, there is a conversion law between frequency and angles. We can say that we have an angular resolution that is given by the wavelength over twice the array length. So the larger the bandwidth, the finer your range resolution. The larger is your array, the finer is your angular resolution. So if you see an array with hundreds of antennas, then you know why. They want to have a very fine angular resolution. Now what we want to do is we want to put the two concepts together and have a system that provides both range and angular resolution. To do that, we just imagine that we have an antenna array where each antenna transmits now a radio frequency pulse, so no longer a monochromatic signal, but a signal with a bandwidth. So this is what we get out of the first antennas: transmission, reception, second antenna, transmission, reception, third antenna, and so on. You see that the delay has a minimum, which corresponds to the position that is the closest to the car. This variation of distance of delay is called in jargon the range migration. And this is a bit annoying to us because, let's say, for the fact that you have this range migration, we should use a more sophisticated algorithm. This is something that we can do, so it's not a real problem, but for the sake of understanding the basics, we will just imagine that range migration is negligible. So we imagine that the variation of delays is so small that if we just look at the magnitudes of the signal, we see always the same thing. So the one variation from one antenna to another is within the phase. So basically, if we look at this collection of 5 signals, based on the position of the peaks along the time axis, we know that the delay is 2R over C. So based on the peak positions, we tell the range, the distance. And we know that the phase of the peaks has a linear variation. So if we get the frequency that determines this linear variation, then we know also the angular position. And this is exactly what we do. This is an example. This is the range data matrix. Now, this thing here is just a simulation of this figure. It's exactly the same. So on the horizontal axis, you have time. On the vertical axis, imagine that you have the signal for each antenna. So now I don't remember how many pixels I do have here. Let's say 100. So on each row, you have the signal at a certain antenna. In this case, I see a peak here, I see a peak here, another peak there, and so I can count 1, 2, 3, 4 peaks, which means that I expect to have 4 targets at different ranges. But then I calculate the Fourier transform, and the Fourier transform is just the same operator we saw that is implemented column-wise. So there is a sum in the vertical direction over the dimensions of the antennas. And now I can see 1, 2, 3, 4, 5 targets. And why? Because I placed 2 targets at the same range. At the same range, but of course at 2 angular positions, at 2 different angular positions. Now, with this in mind, we can finally see SAR imaging. So we start again from the geometrical interpretation. We measure the delays along a trajectory, and so at the end we should be able to localize a target somewhere in this circle, over this circle. Now, how to approach mathematically a SAR? Well, the trick is to think that it is exactly the same as the case of the antenna array we have just seen. With an antenna array, we just imagine that, okay, this is the first antenna, transmission, reception, second antenna, transmission, reception, and so on. For a SAR, you have something that flies, and as it flies, it transmits, receives, transmits, receives. Since the speed of light is so much larger than anything else we can appreciate in practice, you can fairly assume that the so-called start-stop approximation, which means that you can assume that the radar is hovering in air, it transmits, receives, and then it makes a step. Transmit, receive, another step. And so this simplifies a lot. So we have this analogy, synthetic aperture and antenna array. The distance between, so let's say the space between any 2 equivalent antenna elements is called, okay, delta x, and this is given by the pulse repetition interval, so the time between any 2 consecutive transmissions and the velocity. One question that students have the first time they approach SAR is, okay, fine. With an antenna array, I can visualize how long this is. So I have an array of 2 meters. So if I know the wavelength, then I can calculate the angular resolution of this array. But what for a SAR? So let's imagine that you have a satellite, and the satellite flies for thousands of kilometers. So what is the equivalent length of this array? Well, to answer this question, we have to consider that any antenna actually does not illuminate everywhere. So a perfect isotropic antenna doesn't exist. But antennas have a beam width, and this beam width is given as the ratio between the wavelength and the size of the antenna. So for example, for a spaceborne radar, this is the case of RadarSat-2, we have a length of the antenna in the order of 10 meters or even more. The wavelength is some 5.6 centimeters. So you have a beam width. It means that when the antenna is turned on, it illuminates over a beam width of some half a degree. But you can have totally different cases. For example, this is the DTU Polaris equipped with a P-band antenna, so a much larger wavelength and of course a much shorter antenna. In this case, the beam width is over 20 degrees. Now, what does it imply for SAR? Well, it implies that any target is illuminated only for a fraction of the time. You see, in this case, this target is not responding simply because it is outside the beam of the radar. As time goes by, now the radar is, the target is responding, it is still responding again, and then it stops. So basically, the equivalent array length, so the length which we use to compute what is the angular resolution of a SAR experiment, depends actually on the beam width of the antenna. And you see that for a target you see that for a target at the distance r from the trajectory, you have an equivalent length of the antenna beam width times the distance. This length is called the synthetic aperture. And so the synthetic aperture is the length of the equivalent array that you can use to model your SAR, and it depends on the illumination capabilities of the antenna. Now, if this is the length which we have to consider to do all our calculations, by our array theory, so by what we have finished to see just before the break, we can tell that we have an angular resolution of half the wavelength divided by the synthetic aperture. So this is the angular resolution of a SAR system. This is something that you can compute. You can take any spaceborne SAR you like, you know the wavelength. If you Google a little bit, you can find its the beam width, or you can guess it from the size of the antennas and compute the angular resolution of the system. Now, an interesting thing is that the synthetic aperture actually is not fixed. You see, we say that the synthetic aperture is given by the beam width, and this is fixed because, so this delta psi is what I call the beam width. This is a fixed parameter. It just depends on the antenna that you are using, and it's multiplied by the distance. So this means that as the distance increases, also the synthetic aperture increases. So the synthetic aperture is not a fixed parameter, but it is something that changes for every target. You hear that that spacebound system has a synthetic aperture of X meters, but of course, that is an average value, just to have a reference. Keep in mind that the synthetic aperture, by virtue of this mechanism, it has to depend on the distance. So, since the linear resolution is the angular resolution times the distance again, it means that for a SAR, you have this linear resolution, so your delta X. And if you put all the equations together, you will get to this result that the resolution, the linear resolution for a spacebound SAR is more or less, with some factors that depend on antenna technology, half the length of your antenna. So for example, we saw an example with radar SAT before. We say that the antenna was some 10 or 15 meters long. Well, the resolution cannot be too far from about 6 or 7 meters, because this is more or less the order of magnitude. This one, I can skip it. Okay, so now for the third time, we go back to our geometrical interpretation. If we just use geometry, we have to conclude that after a SAR experiment, we can localize the target on the border of this circle. But okay, this is something that we say that 9:30. Now it's 11:02. We have seen a lot of physics. We have seen a lot of principles by which we can talk about the range resolution and the angular resolution, which for a SAR becomes a linear resolution or an along track resolution. And so we can do better than that. So we can attach the concept of resolution, and this is what we do. After a SAR experiment, you can tell that a target is somewhere within this region of space. Let's say it's a sort of a motorcycle tire. The width in, let's say, the thickness is given by your range resolution. The width is given by your along track resolution, delta X. The along track resolution is also called the azimuth resolution, okay, just a jargon. And this basically means that when you look at the SAR image and you consider a certain pixel, okay, and you find the value, you need to keep in mind that that value is the result of everything, so of every target, every object within this region of space. This is the concept of resolution cell. And this is exactly what this, the next 2 or 3 slides are trying to convey. Imagine this is a SAR image. So for each pixel, you read a number. The blue pixel means that you have is the contribution of everything within this region. So in this case, let's say there is just a car. And so we see a blue pixel. In this other case, we have several trees. And so we can tell that that pixel, the green pixel, is the result of the interference of all of the trees within this resolution cell. So this is how you have to read the SAR image. Remember that every pixel is not, so it's not what is in that position. It is the result of everything within this resolution cell. So this region of space, this sort of motorcycle tire attached to that pixel. So you see a SAR image and you need to think about motorcycle tires. Having said that, tomographic imaging. Now we want to do even better than that. So we want to enter inside the motorcycle tires and split it in several subcells or in several boxes. I need to introduce some jargon. So A tomographic experiment is the result of flying several trajectories. This is called in jargon a multi-baseline experiment. And why this term? Because the interferometric baseline is defined. So if you take a look at this picture, you rotate it so that the satellites are flying perpendicularly to the board. The baseline is defined as the vector between a certain reference satellite and any other satellite. And the normal baseline is defined as the projector of this vector perpendicular to the radar line of sight. So this is called the baseline. So if you have two satellites, this is a single baseline experiment. If you have many, this is a multi-baseline experiment. Now, the trick to understand tomography, not just from a geometrical perspective, but from a physical perspective, is to understand that the ensemble of all the satellites for a fixed along track position is exactly the equivalent of an antenna array. But this time it's not horizontal, it is vertical. So it's not an equivalent array along your orbit, but it's in another plane. It's, let's say, perpendicular to the orbit. With an antenna array, we have an angular resolution, so we can resolve different angles, and in this way, different elevation angles. Again, we can attach some numbers. Let's say that for each resolution cell, you see, we can, let's say that we can now split the resolution cell attached to any pixel to different elevation angles, and we can put some numbers on it from array theory. So this is just the theory we saw until before the break. Let's say that we have a total baseline aperture of BAP meters, and then we know that the angular resolution is given by half the wavelength divided by baseline aperture. So if you have a set of 10 satellites or 10 orbits with a certain baseline aperture, if you know the wavelength, you can immediately calculate the angular resolution of your instrument. And this angular resolution, of course, translates to a linear resolution. You just have to multiply by R. So the first question can be, I need to resolve the terrain below the forest and the top of the forest at the height of 30 meters. Okay, this means that you need to ensure that the two beams allow you to separate something at 30 meters apart in height. Let's see how to get it. So how to interpret TomoSAR cube. So we no longer talk about an image, but this time we have a cube. So let's say that a cube is a collection of images. In this case, for the same pixel, we have the gray. So for the same SAR resolution cell, we have that the gray pixel in this lower layer is the terrain, and then we have the red one is the red one is, okay, in this pictorial representation is the first tree, and then so on. So this is how you read the tomographic cube. Every layer is a SAR image, which is just obtained with a very narrow beam. And the different layers correspond to different beams. This is just to summarize. At the end of a tomographic SAR experiment, your resolution capability is given as follows. So just imagine that the bluish balloon is your resolution. you have the size of this bluish balloon is given by the bandwidth of the system in this direction, by the length of the synthetic aperture in this other direction, so perpendicular to the board, and by the baseline aperture along elevation. So with this knowledge now, you could say, let's say that you have enough knowledge to design the basic parameter of a tomographic SAR system to get a certain extent of the resolution cell. What we need to do now is to, let's say, you have a practical this afternoon. And the practical means that you will play with a computer, you will get some data, and you will process some data. Now, I really hope that I got to convey the physical principles behind SAR and TomoSAR imagery. But of course, this is not enough to, I mean, sit before a computer and do the real things. So the next slide, so the next more or less 14 minutes or so, will be about deriving some details of tomographic processing. And so if I do my job well, at the end, it will be easy for you to understand what the code does and possibly how to replicate it or how to modify it. So we start from this in mind. Let's say that we have this situation where we have two satellites and both are looking at the same area on the Earth's surface. And those two lines indicate the SAR resolution cell. So meaning that I am considering a certain SAR pixels such that it refers to this region of space. Now, we saw that each SAR pixel is contributed by many targets. And so I indicate the SAR pixel as IN of Rx, so the pixel from the acquisition number N, we have 2 in this case, at the particular position Rx in the SAR image. So R and X are the index of the pixel in the SAR image, and N is the index of the satellite, let's say. And I need to write a summation. So there is a sum over Y and Z, which means that I am summing everything within this region. Y and Z, well, Y, well, it is simple. So it's just a simple Cartesian system. And I need to keep in mind that the particular target at the general position Y and Z contributes with a phase. And this phase is given by 4 pi over the wavelength times the distance. So you see the phase is always proportional to the distance. And this is the very basics of SAR. And as before, we need to write down the expression of the distances. So in this case, I have square roots again. We don't like them, so we need to linearize somehow. And this is exactly what we do in the next slides. So the trick that we assume in tomographic processing is that we define for each pixel a sort of a reference position. So let's say that we take some SAR pixel, well, this one, and we assume that everything is concentrated at a certain position that we pretend to know. So like, I don't know, maybe I have an external digital elevation model. And so I say, okay, let's pretend that everything is at this position given by this digital elevation model. Or if I don't, I know that the Earth is more or less spherical, so I can try to predict where the elevation is. Anyhow, I take this reference point, and what I do is I try to linearize the expression of the distance with respect to this reference point. What I get again is just, so it's a simple mathematical trick. When you linearize a distance, you always get sines and cosines. I just let you do that, but it's a simple trickery. And we get this expression. So we have that the horizontal distance of a true scatterer with respect to the reference point is multiplied by the sine, and the vertical distance is multiplied by the cosine. We do the same for the other satellites. And so, of course, we have the same approximation, but with different angles. And then what we do is that we take the difference between the two approximations. So we take the difference of the differences. And for this reason, when you study SAR interferometry, you often hear to the notion of double difference. Some people say that SAR interferometry is a double difference thing. This is what they mean. So there is a difference with respect to this reference point, and then we take the difference of the differences in two different satellites, and this is it. What we get is, with some approximations, is that we have the difference between the two angles, the two elevation angles for the two satellites, that multiplies the cosine of reference satellites. Oh my, okay. I'm seeing now, okay, I'm sorry. I'm seeing now that I have cosine of theta m, and then I have sine of theta n. So my apologies. Of course, there is no sense in this. It is the same angle. I am computing a difference, so I am approximating with respect to one satellite. So it should be cosine of theta m and sine of theta m, and not n. So sorry for that. I'll try to correct this and upload the slides again. Anyhow, this is what we have. And it turns out that this long expression is just equal to the difference of the two angles times v. What is v? V is the displacement of our target, of the true target, with respect to the reference point in the direction of elevation. So it turns out that we have a residual term that we cannot explain in terms of the reference position, and this residual term is proportional to the elevation position of our target with respect to this reference point. And at this point, we can also rewrite the difference of angles in the usual way and say that, okay, so we have this expression, and I prefer to just jump to this slide. So what we have done, basically, with some approximation, we came to describe a SAR pixel in this way. We know that it is that a SAR pixel senses the contribution of everything within this resolution cell, and so we express it as a sum. We had a sum over y and z in the first slide, but now that we have worked out the mathematics a little bit, we see that since everything depends on just elevation, so since we got to see that we can approximate the difference of the distances just with reference to the elevation position of the target, now it becomes more convenient to do this sum in this new coordinate system, so in range and elevation. So I just imagine that I am summing now all the targets this way. Of course, the targets come with their phase, but we have just demonstrated that we can approximate the phase in this way. Basically, it is the distance in this way. And so it is the distance of the first, from the first satellite, plus a term that depends only on the elevation coordinate. So this is our model of our SAR pixels. So this is how we write mathematically a SAR pixel. And we can single out different terms. We see that this term here is common for all satellites. So there is no dependence on n, on the index of the satellites. It is the same. So it is a good idea to get the sum over r prime, which means that in this integration, we imagine that we do the sum in this direction. And we have this new model. This model now, we can see it in this way. We have a first term. It is external to our sum. And this term depends on the phase due to the reference position. The reference position is something that we assume to know because we have decided that to take this particular reference position. So this phase term is something that we can cancel out. We know it and we take it out. And then we have those other interesting things. This S of V. This S of V is a signal that depends only on elevation. And it was obtained by taking the sum of that A R prime V times blah, blah, blah. We took the sum with respect to R prime. Now, mathematically, when you have something in 2D, so just imagine that you have something that varies in X and Y, and you took the sum over in one direction, so you get a signal that is a function of just one variable. This is called the projection. Just imagine that you have 2D things projected. Now, this is a function of just the vertical direction. This is exactly it. Don't do this when the water is inside the cap. Anyhow, so this S of V represents the projection of the scatters along elevation. And we can attach a physical meaning to it. Always remember, the SAR pixel is everything in this region of space. When we project it, we get something like this. You see, this is the projection of the terrain. This is the projection of the three canopies. So we can imagine that our SAR pixel is contributed by this one-dimensional signal as a function of elevation with a very strong physical meaning attached to it. And indeed, we can now understand tomographic processing. What we do in practice and what you will do this afternoon in the practical is exactly to take a bunch of SAR images acquired from different sensors. And then you say, okay, let's do tomography at this pixel. What you do, you take a sort of a carrot. So you take like a vertical, so you take the same pixel in each image, and this is your mathematical model. You know that this pixel is contributed by the projections of the target. Each particular, so the object at a particular elevation V comes with its phase, and the phase is again linear. So a linear phase means that we can describe it as a frequency. So you see now we have a frequency This is the conversion law between frequency and elevation. But again, we are saying that the collection of the SAR pixels from different images is a signal that is contributed by different frequencies. And each frequency, so the amplitude of each frequency is represent the strength of the target at that particular elevation position. So again, by a Fourier transform, we will be converting a stack of SAR images into a tomographic cube, meaning that we single out the amplitude of each frequency, and the frequency have a direct physical meaning because they are directly converted to elevation positions. And this is what I just said in a slide. And so now this is our tomographic algorithm. This is exactly how it works. We take the stack of SAR images and we do the Fourier transform. Now, if you look at your slides, you go back to the first slide where we introduced the Fourier transform, you will see this is exactly the same mathematics. So we did it first in time. So first the Fourier transform to pass from time to temporal frequencies. Then we assumed the case of an antenna array. And so we did again a Fourier transform, space to spatial frequency that will convert to angular positions. And now we are doing this for the third time, and we pass from baselines to elevation positions. You see, it's everything about passing from time to frequency or space to frequency. Just some example. Let's say that the black dot is my reference position. I just analyze the region of space that corresponds to one resolution cell, and let's say that I have a true target. Where is the red position? So now this is the projection. So I know that the signal is contributed by a single frequency. Of course, I need to attach some resolution to it. And this is it. So I do not have a perfect narrow peak, but I have some spread. And this is the equivalent of the bandwidth. So since the baseline aperture is limited, so the observation space is limited, then the bandwidth is not zero. In the case where I have 2 points, of course, I get 2 peaks. And I can say that I can resolve them as long as their difference in elevation positions is larger than this value. This is the case for a terrain. So keep in mind that the terrain is an extended thing. So it's not just a point. So when you take the projection, you have some spread, which, by the way, will depend on the terrain slope. Okay, this is not very important. And then this is it, and this is the case for a forest. We have a terrain, we have trees, we get the projection, and so we expect that our Fourier transform will produce some signal for the terrain, and then some signal that represent the forest canopy. This is just to sum it up, and also to make you aware of the fact that many, let's say, large part of the literature doesn't like to talk about elevation, but they prefer to talk about height. But this shouldn't trick you. It doesn't mean that they are resolving targets in this direction. They always resolve target in this other direction. And the trick to pass from elevation to height is just to consider this representation. So the true targets are, so the target that exists in the real world are projected to get you something just in elevation, and then you do another projection over height. And this is what you get. It is customary to rewrite also the phase term in this way. So you can surely notice that the vertical displacement is given by the elevation displacement multiplied by the sine of theta. And so this is embedded in the phase, in the mathematical model of the phase that is now cast with respect to Z in this way. This KZ is called the phase to height conversion factor, or the interferometric wave number in some case. So if you happen to read a paper about like SAR tomography, you will hear this, you will see this guy KZ many, many times, and this is it. Okay, now just a word about the phase external to the sum. We say that the SAR pixel also has a phase term that it refers to our reference position. Well, this phase term determines where your signal will appear. Just imagine that the true terrain is the yellow one. But for some reason, you did your processing with the wrong terrain model. For example, because you had to use a terrain model from an older instrument, or it was not accurate for any reason. So let's say that you are doing your processing with this terrain model. So what will happen is that what you have to do, so this becomes your reference position. You take the projection, and this is how your tomogram will appear. Of course, you can further project it over. This is not a projection. You can further cast it over height. Basically, this is your zero. This is where you think that 0 meters is, meaning that this is where the reference terrain elevation is. Since it is wrong, there is nothing here. And you will see the terrain to be up here. If you know the true terrain elevation, now you use the right one, and then your terrain will appear in 0. Now, let me tell you that for the case of a dense forested area, it's not, so the true terrain elevation is not known a priori. We just don't know it, and it will be a task for the biomass mission to tell true terrain elevation under the below the forest, everywhere in densely forested area. This is, by the way, something that we are about to start working on with Laurent and with DLR. So let's say probably at the next advanced course, we will know better where terrain elevation is in tropical forest. Now, the last argument of today is about ambiguity. Ambiguity is a big thing for radar experts. And let's say many times we spend a lot of time stretching our heads on how to get rid of ambiguities. What is an ambiguity? Basically, you can imagine that in a radar image, along with the peak or with the bright points that are associated with the target, you also have ghost targets. I mean that you have peaks, fake peaks, that do not correspond to real target. This is something that engineers take great care about, and this is a problem very important for SAR tomography. Because for SAR tomography, for the simple fact that we cannot collect the signal in this direction in a continuous fashion, but we have one orbit here, the other orbit is there, and so on. So for the simple fact that the coverage is not continuous, then we have ambiguities along elevation. So just imagine that this is the result of a tomographic processing. We have the true tree, the green ones, and then we have fake trees that are here marked in red. Now, to understand where this comes from, we can take the simple case where the baselines are uniform. So let's say that I have a reference flight, and then I have another flight at the normal distance, delta B, another one at the same distance, and so on. So we call this a uniform baseline distribution. And since it is uniform, I can write in place of Bn, which is the baseline for the acquisition number n with respect to the reference acquisition, we can write it as delta B times n. And now you will see why this is important. So let's analyze the phase. Let's say that we have a target, a true target, at some elevation V0. So the phase for the acquisition number 0 is 0, because n is a 0. For acquisition number 1, we have some numbers, and we represent this in the complex number as an arrow that from some phase with respect to the horizontal axis. Acquisition number 2, we have yet another phase, and so on. Wonderful. But now let's consider another elevation that is given by this formula. Do not concentrate on this formula now. Let's just say that it is possible to get an elevation this way. And I picked those numbers exactly because with this elevation, you get phases that are exactly the same as in the first case, up to an integer number of cycles, so up to an integer number of 2 pi's. And of course, when you measure an angle, if the angle is 0, or if it is 2 pi, or 4 pi, or 6 pi, it doesn't make any difference, right? And so in this case, we have that 2 targets at different positions. One is at V0, the other is in V0 plus VA. They correspond to exactly the same phases in all acquisitions. So they cannot be distinguished. And for this reason, we have an ambiguity, and indeed this subscript VA, it's not a subscript here, stands for elevation of ambiguity. So we should revise our theory in this way. This is the case of a single target. Actually, this is what tomography will give you. So it will provide you with a peak with some spread, and this is due to your resolution in elevation. And then you also have the ambiguous targets. You have ghosts that come at the distance VA from the true peak. Now, some baseline tip. The important thing to notice is that your elevation resolution depends on the total baseline aperture, whereas the elevation of ambiguity depends on the spacing between the baselines. So what you would like to do is to have a system with a lot of resolution, so a very fine resolution, which means that you need a very large baseline aperture. but you would like the ambiguities to be very far from you. Maybe a thing that I didn't discuss enough is, when is an ambiguity harmful? Well, let's say that this is a forest. So if the elevation of ambiguity comes at 500 meters, this is not a problem, because you are absolutely sure that it's impossible that there is a forest floating up in the air at 500 meters. So yes, there is an ambiguity, but come on. If you have a forest that is, let's say, you expect a forest of some 40 meters, and you have an ambiguity of 20 meters, oh, this is a big problem, because it means that you have a replica of the terrains every 20 meters, or you have a replicas of the top of the canopy every 20 meters. So everything is mixed. You can no longer distinguish. So, ambiguity depends on the baseline spacing. So you would like this baseline spacing to be as short as possible. So basically, what you want to do is a total baseline aperture that is as long as possible, and baseline spacing that is as short as possible. So since the number of passes, of elements, of orbits that you need is the ratio between baseline aperture and baseline spacing, it means that to do tomography with a fine resolution and a good height of ambiguity, you need a lot of passes, you need a lot of orbits. And just to give you some numbers, we closed last year a campaign with ESA. It was called the TomoSAR campaign. We didn't want to have any problem related to ambiguities, and so we had to fly more than 20 times. So we did tomography with some 20 baselines. Some tips to determine how many passes you need. Okay, this is it. Let's say that for a forest, it's a good practice to have a height of ambiguity that is roughly twice forest height. So let's say that you have a 30 meter forest. You would like the ambiguity to stay at no closer than 60 meters. Let's say that you want a resolution of 5 meters, then you need 60 over 5, 12 passes. And this is more or less how you reason to design a tomographic survey. Unless you go for some sophisticated technique that exploits a non-regular baseline distribution plus some signal processing trickery, which you will see with Laurent Ferrofamil in the this afternoon. Okay, so for the moment it seems like I'm done, but I want to spend the last less than 5 minutes to talk about the TomoSAR campaign. This is a campaign that was flown in 2021 at this site here. This is the Eiffel Park in northwest Germany, and this is in particular is the Kermeter area. And we had a big campaign with ESA where basically we flew P-band, L-band, and C-band. They are all fully polarimetric data. So we have a big data set. We passed for each frequency band about 20 times. So we can do tomography at a fairly good resolution at different bands. And we flew with 2 aircraft so that we have one acting as a transmitter receiver, or the other configuration is that one is transmitting and the other receiving. And this is called the bistatic configuration, which has some interesting features. This campaign came with the collection of in situ parameters at approximately 80 plots. And by in situ parameters, I mean like forest height, forest density, tree species, if the tree is dead or not. We have terrestrial laser scanning data. So they went there, installed this machinery to provide you with a very high with a centimetric resolution of the forest plots. I think at the scale of about 1 hectare. And we also have aerial LiDAR. And so we have the terrain, so the true terrain topography. We have the top of the canopies, and the biologists worked together to generate a forest biomass map. So those data also come with a reliable estimation of a forest biomass. And the good news is that as a part of the deliverables to ESA, we produced a data set that is already calibrated. So let me say it's perfectly calibrated, but of course I cannot assume that our work was perfect. So it's decently calibrated, which basically means that we took care of all the subtleties of radar processing. And you can process this data exactly as we discussed today. So there's nothing more to do. If you don't want to start from radar images to do your own tomography, we already produced the tomographic cubes for you. So you can simply take our tomographic cube and compare them with LiDAR forest height or with forest biomass. You can do like a multi-frequency regression. You can try to see if P-band or L-band is better correlated to forest biomass. You can do a cross-analysis with forest species and so on. And if you want this data set, all you need is a fast internet connection, because it's about, if you want the radar data, I think it's about 400 gigabytes. But if you're happy with just the tomographic cubes and reference data, it's much less. There's no FTP, but if you send me an email, I will reply with another email with the link. Okay, this is it. I thank you so much